the topic of planetary defense. Been involved with this practically from the time that I joined aerospace. I was born in Jerusalem, Israel. Did my undergrad and master's at the Technion in Israel, and came to the US to do my PhD at Georgia Tech, where I did not do anything that is related to asteroids and planetary defense. So this endeavor started when I joined aerospace quite immediately. Initially, it was mainly for curiosity. It's cool to work on asteroids and stuff. But over the years, I recognized that this is one of those big items that could change life on Earth. And so I became more involved with the topic over the years. What I'm going to do now, I'm going to essentially go over several web pages that introduce the topic of planetary defense for those that are not familiar with the hazard, and present a couple of the works that we've done here and a couple of the activities that we are doing quite routinely. So that was just an introductory page about myself. If you have any questions, please put it in the chat. I may not be able to see it, but Svetlana can interrupt me when there are some questions in the middle, and I'll try to answer them briefly. And I'm happy to stay at the end to answer additional questions. This is a NASA page, webpage that is dedicated to planetary defense. All of the topics that are related to planetary defense are covered here, including discovery and missions and resources. Very interesting page to visit. That page is typically where I go to answer the question, well, what is planetary defense? It is the term used to encompass all of the capabilities needed to detect and detect the possibility and warm of potential asteroid or comet impacts with Earth, and then either prevent them or mitigate their possible effects. So I will show some of the studies that we have done and are doing on the topic. It's a very interesting page to visit, and I encourage you to go and visit this page. We will visit this page throughout the presentation and encourage you to go and visit it. Another interesting webpage is a page maintained by the Jet Propulsion Laboratory, JPL. It is a one-stop shop for everything asteroids and comets. I'm using this resource extensively, and we are going to visit this page several times during the presentation. It talks about breaking news about asteroids. It gives a lot of statistics and late-breaking results about the asteroids. So we are going to visit this page also during our presentation to see what's going on around the planet right now as we speak. And that is a planetary defense website that we have developed recently at Aerospace. It celebrates our collaborative work with JPL on several counts. So we have developed teaching aids on planetary defense and asteroids that are tied in with the next generation science standards. You can visit this page here by simply going to this link and read about what we do, the tools that we use with some demonstrations here. There are some lesson plans that are geared to the K-12 science teachers and the students, so the teachers can use those resources to teach. And you can see what careers we are looking for at Aerospace. And as a result of our activity, we landed in an IMAX movie that has been produced in the last 3 or 4 years and is now ready to deploy at international IMAX theaters. It is just waiting for the pandemic to ease up a little bit. And so I'm not going to play the trailer here, but the movie is going to come out in the next few months. And you can see us in the movie. contributing to the movie. It's a fascinating movie to introduce the topic to family and kids and to the world community, in fact. So that's the trailer of the movie here. We also developed a NEO deflection app. NEO is the term used for near-Earth objects. Those are asteroids and comets that orbit the sun just like we do, and their orbits potentially could bring them close to our planet, too close to be comfortable. So we need to keep an eye on them and try to detect them and find them before they find us, as they say. And so we develop a physics-based app that I'm going to demonstrate. Its usage both at conferences, workshops, and also at STEM workshops. Some of the studies that we do involve artificial intelligence that was applied to find asteroids from archival pictures of the sky that were taken, and also to inspire the next generation of scientists and engineers. I've inspired my son, and we wrote a paper together that can be accessed here. And I'll show a newer paper that we wrote recently and published on the topic of planetary defense. My son is studying political science, so it kind of injected me to bond with him and kind of combine the technology and the policy aspects of planetary defense, and we are working together now as a team. So going back to the NASA page that I showed earlier, very recently, Juno's mission visited Ganymede, which is Jupiter's moon, took this fantastic collection of pictures put together, demonstrating that we are not alone in the solar system suffering impacts over millions and billions of years. So the effect of asteroids is felt across the solar system. And I thought this is just a fantastic picture to show that we are living in a shooting gallery, essentially. Similar fate exhibited on the moon. Anybody who took a basic telescope to look at the moon easily observed the multitude of impact craters on the moon, sometimes nested craters. And so the moon and us are living in the same neighborhood, and we suffer the same fate and same likelihood. Most of the evidence on the Earth was erased over the years because of geological activities. But just looking at the moon, we know that the moon and the Earth suffered a fair amount of impacts by those objects. Some of these objects actually do impact with our planet. They are called fireballs or bolides. And the JPL maintains a database of those fireballs that were detected over about 3 decades of use of government and sensor data that looks for explosions in the atmosphere. As of fairly recently, 867 entries were detected and put into this map. Most of them occur over the ocean or uninhabited land. Some of them are quite energetic, as you can see here. And we are going to talk about 1 or 2 of these later in the talk. But one of the takeaways from here to see is that the distribution is fairly uniform. There is no one area that is particularly favored over another. And it's just down to the sheer size of the country that would suffer the majority of those impacts. Likelihood of 2 to 1, it's going to be an ocean entry and won't be seen by anyone except government satellites. So over 3 decades, about 867 entries were detected, but more recently, some additional resource was added to detect those based on geostationary satellites that look at lightning activities. And over about a couple of years, they were able to detect over 2,300 of those explosions, which tells us that we were severely underestimating the phenomena. And we would like to understand, based on observable collisions with the Earth, to understand the risk of being impacted by some of those bigger objects that can cause actual damage on our planet. So the question would be, what happens if a bigger object that is not trivially small would be approaching our planet undetected and just about to collide with our planet? What could we do? So we conducted a small study here. Could we intercept an asteroid just before its atmospheric entry and disrupt it? So that is a quick review of a study that we've done. What we've done here is we are based on the well phenomena that occurred about 8 years ago over Chelyabinsk. There was an explosion by a small asteroid that released its energy at a very high altitude. It caused some injuries on the ground and injured over 1,000 people, caused significant damage on the ground. If that object had been entering at a steeper angle, the damage would have been much, much larger. And that was a wake-up call that even small objects could cause significant damage on the ground. So here is the general phenomena. If we would not intercept the object, it would release its energy at a fairly low altitude and could create severe ground effects over perhaps a key installation with damage to life and property. We would like to attempt to intercept that object at a higher altitude and disrupt it and distribute the energy over a larger area. And so that is the nature of what we were studying. We would like to either break it into smaller pieces with larger surface area that would release the energy and save the day over one of those key installations. So we devised a sequence in which the object will be detected literally minutes before atmospheric entry. A firing solution will be calculated, an interceptor will be launched, and will intercept it and try to disrupt it at several kilometers before atmospheric entry, such that it will release its energy at a higher altitude. And we used the information from those bolide map to come up with the statistics of a smaller object and try to project it into the bigger object. What could be expected from a bigger object that might be appearing out of nowhere, as the Chelyabinsk example shows. So we did some trajectory calculations based on the timing of the event, and everything here is measured in minutes. I'm going to skip this for now and skip this for now. These are just results of our simulations. And what we want to do is to pick existing technology for intercepting those objects and use existing expertise to conduct that mission. We assume that we have a technology that can be adapted out of Minuteman or the THAAD ballistic interceptors. Same technology and same level of kill vehicle masses were assumed in that study. And also we showed that the object can be intercepted by the use of similar missiles. And we also calculated or based calculations on where the majority of the energy would be disrupted. And based on simulations and measurements, most of the energy without any interruption would be released at altitudes between 20 and 40 kilometers. and cause the majority of the shock wave and the heat wave on the ground. So we would like to intercept this at much, much higher altitude, and we found that it is actually possible to do that at altitudes of hundreds of kilometers. So that is definitely sufficient to develop a disruption on the ground. And so what we've done is we said, okay, if we were able to intercept the object at an altitude of several hundred kilometers, what will happen to the object upon being intercepted by the kill vehicle? We looked at several scenarios, and we ran hydrocode simulations and tried 1 ton and 5 tons and 5 shots of 1 ton, and then 2 shots of 1 ton and several tons with explosive material on board. And we showed that we could actually disrupt it partially or completely if we do 5 1-ton series of collisions. We can actually see we can completely incinerate the object. Here is an example with explosive material, with a couple of intercepts, and with 3 intercepts, we were able to actually penetrate into the object and cause the explosion to occur inside the object and completely destroy it. So this is a study that we've done. Our next phase, hopefully, will be to calculate what will be the improvement in terms of the ground damage. We haven't done it yet. So we did 2 out of the 3 phases that we were planning to do on the study. So if we get some funding, we can do the last part and say, if you build that system out of existing technology, here is what you can do to save the day over an installation that could be a major city just about anywhere. So moving forward to see how many impact craters were identified on the Earth, it's almost 200, over 190 confirmed craters were detected on the Earth. Some of them are quite large, obviously over millions of years. These are very, very, very rare events, so there's nothing to be worried about in the very near future. But the smaller objects definitely impact us very, very routinely. So this is going to be one of those things that we need to keep an eye on. So I invite you to go and visit this Wikipedia page. It has nice resources to those craters and the stories behind them, and studies that were done to understand when and where and what occurred during this time. But the most famous area is obviously the Chicxulub crater. It's the area where a big asteroid impacted in the Yucatan Peninsula and caused the extinction of the dinosaurs. Again, a very interesting webpage to read. It was calculated to be an object of about 10 kilometers or over 6 miles in size. And the reason why it was discovered or concluded that this was the area is because the oil companies are looking for gravitational anomalies in the Gulf of Mexico for the best place to dig for oil. They found those circular shapes in the bottom of the ocean, and they concluded that the only thing that could cause these regular shapes that cannot be attributed to any geological activity is a big impact by an asteroid or a comet object. And you can read about the research that was done about the discovery of a region in Italy by Berkeley geologists that went to study the magnetic field of the Earth. And they found this limestone that was separated by a layer of ash. The limestone below the layer of ash was abundant in dinosaur fossils, and none was found above that layer of ash. And they calculated that this layer of ash was rich in iridium, which is typical element found in asteroids or in meteorites that fall on the Earth. So that was a mass extinction event that occurred some 66 million years ago. And recently, I read that they excavated materials from the Yucatan Peninsula area and found that it was also rich in iridium and dated to the same time. So the pieces of the puzzle are coming together as to the extinction have been caused by, at least in part, by an impact by an asteroid, a large asteroid or comet, that potentially also cause shockwave that traveled across the planet. So the other focal area in India, there is an area with volcanic eruptions that was periodic over millions of years. And at the time of the asteroid impact and the extinction event, the rate of massive volcanic eruptions has doubled. So there are several pieces that seem to come together here as to a class of phenomena that caused it. Obviously, a 10-kilometer object is calculated to occur perhaps one every maybe 100 million years. And so we shouldn't be worrying about any object like this colliding with us anytime soon. I'm going to show the rate of discovery of this object as of today, but it's good to keep an eye on the object that we are aware of as of today. Moving forward in time, we look at the Meteor Crater. Meteor Crater is probably the best well-preserved impact crater in the world. It's located in the state of Arizona, not very far from the Grand Canyon. So if any of you is planning to go on a trip to the Grand Canyon area, I recommend to go and visit in the central North Arizona here, which is not very far from the Grand Canyon area, and spend a few hours at this visitor center, read about those objects that came from outer space, and take a tour to the edge of this very nicely preserved crater here from the visitor center, walk around the edge and appreciate the force of nature that was created by not very, very large asteroid. It was about a 50-meter asteroid, about 150 feet in size. So not a very large object, caused very significant damage. An object like this that would explode over any major city would completely incinerate the city within milliseconds. Moving forward in time to the very famous Tunguska event that occurred in the year 1908. It was a similar phenomenon, except that this object of a similar size exploded in the atmosphere and did not create a crater on the ground. It basically flattened about 2,000 square kilometers of Siberian desert and flattened the trees away from the epicenter of the event. Similar phenomena, if an event like this would have occurred over any major city, the big city would be destroyed instantaneously. As an example, Moscow is in the same latitude of this area, Tunguska, and if the event had occurred just 3 hours later, Moscow would have been obliterated simply because of the rotation of the Earth in 3 hours' time. So that is part of the kind of wake-up calls that we are aware of over over a recent history. Very recently, there was another event, the Chelyabinsk event that I mentioned a few minutes ago. Again, occurred over Russia. There's nothing special about Russia except that it's the biggest land country on the Earth, so it probably suffers the majority of those objects that are detected. It exploded over the city of Chelyabinsk, injured over 1,000 people. And it was captured by a multitude of dashcams. I will not play that here for the benefit of time, but invite you to go and visit this Wikipedia page and other pages that are linked from here. Very fascinating event that occurred just 8 years ago, and it is calculated that an event like this is roughly occurs perhaps once or twice in a century. So within our lifetime, an event like this could disrupt your local region. Low likelihood, again, it's a low likelihood, but I think you wouldn't board a plane that will have that likelihood on it of crashing. So now we have a few examples of those objects. Let's see what's going on our planet right this minute as we speak. So I'm going to go back to the JPL webpage here and look at the close approaches that occur right now. Here is today, July 15. We have an object. It's a small object. It's about the size of the object that exploded over Chelyabinsk. And it is passing next to our planet at a distance of slightly further than the moon, 1.24 lunar distance from us. That is a concern. I mean, nothing, obviously, there's not going to be any damage that will occur to our planet because no collision, but that is a very close call. And looking forward into the next 60 days, we see that there's a multitude of objects that are going to pass by us. Some are closer, some are further, some are quite large. There are some objects that are in the hundreds of meters that have been discovered this year, earlier this year. What could we do if an object has been discovered with weeks or days or months prior to impact with our planet? Potentially, at best, we can do a disaster management, evacuations, disaster response. We definitely do not have any system on the ground currently to address any of these objects that are making routine close approach to our planet. Some of them could be quite large. Here is a very large object in the kilometers. It was discovered in 2016. So we do have about 15 years to, well, not 15 years, 5 years, to deal with it. Can we do something in 5 years? If we are prepared, if we have pre-developed systems, perhaps we could do something. But we know that to build and test those launch vehicles and space vehicles is not a trivial task. So 5 years is kind of borderline as to what we could do. Here's an example of an object that gives us about 10 years. 10 years is probably a comfortable zone to build systems and attempt to disrupt it and kill it or deflect it. I'm going to do a little exercise here just to see, to kind of narrow down the focus on this object. So what I'm going to do here, I'm going to expand the range and look at all available data. So it will take a minute or two for the JPL engine to process all available data here. There's going to be thousands of objects appearing here on the map. And then we are going to narrow down the objects to those that might most be concerning to us. So it will take another few seconds, I'm hoping. Maybe by the time to let this process going, I'm going to, oh, okay, it just completed. So we see we have almost 30,000 entries on this table here. Obviously, this is a very large number of objects. So what I'm going to attempt to do, I'm going to say, let's look at just those objects that pass at less than the distance to the moon. So I'm narrowing down, and now I'm down to over 800 objects that are passing, have passed or will pass by our planet at less than the distance of the moon. Some of them are very, very close, 0.13 times the distance to the moon. And there will be even objects that are going to pass even closer than that. So let's narrow it down further and look at objects that are not trivially small. I'm going to increase the size of the objects to see how many of these can cause significant damage. Over 100 are measured in the dozens or hundreds of meters here. Let's narrow it down a little bit further and take a look at bigger objects. So we have 39 objects that are in the dozens or hundreds of meters, passing at a distance closer than the moon here in the next years and even decades. Here is one that is passing below the satellites. 0.09 is below our satellites. Let's see, what do we have here? Yeah, okay. Let's go to 2029. This is probably the most famous object. It's going to be in the news big time. It's called Apophis. It's going to pass below the geosynchronous satellites in the year 2029, April 13. And I'm sure that there's going to be some missions that are going to be launched toward this object to characterize it, maybe even collide with it, take some pictures, selfie with an asteroid. Big event that is building up now. It is not going to collide with us, and it's not going to return to collide with us in the near future, but we definitely need to keep an eye on this object and these other objects here in case they happen to return. All of these objects are on a cyclical orbit around the sun. So it's like a clockwork that eventually will bring those objects into close proximity with our planet. And that's not a trivially small object. It's in the hundreds of meters, about 300 to 400 meters in size. So definitely it's going to be an interesting event. So how many objects are we aware of as of today? JPL maintains a nice database and a graph here on the number of objects that are known to us as of today or a couple of days ago. And they have over 26,000 near-Earth objects on this plot here. It's divided into the really big ones that are marked in red, and then those that are 140 meters and larger than everything else. Obviously, you can see the rate of discovery is accelerating. With more telescopes put into action, we are finding more and more of these objects. We are not finding almost any of the real big ones here, which is good news. And all of those objects that are larger than 1 kilometer are not projected to impact with us in the next century or so. So we will leave the problem from the big objects to the next generations of scientists and engineers and planetary defenders. But we are definitely much more concerned with those that we don't know about, which are the majority. Obviously, the plot is not flattened out yet. Probably will take maybe a few decades until we will see a phenomena that this plot will kind of flatten out into probably hundreds of thousands of objects at some point. And so we really live in the dark ages in terms of objects that can destroy a city or a small country as of today. And that table here is just a small fraction of those objects out of this 26,000 objects that I am showing here. So this is just the reality in which we live. This is a reality of objects that could collide with us with very little or no warning. All of the objects that are discovered and confirmed are put into this database maintained by the Minor Planet Center with their best statistics. And you can go and retrieve the data from there and do some studies on the most latest discoveries. And this is a good resource for a lot of those objects. How do we find them? So obviously, to find those objects, we are using ground telescopes and looking for dots of light that move in the sky across the fixed stars over clear night skies. But recently, NASA approved moving forward with a mission. It's called the NEO Surveyor. It's going to be an infrared technique to find the objects based on the heat emanating from the objects. I think that based on this page, it's slated to launch in 2026 and will probably increase by an order of magnitude the rate of objects that will be discovered in this mission. So this is a nice page to visit on the same NASA webpage to read about the spacecraft and the mission and how it is moving forward. Also, later this year, there's going to be a very interesting mission that is scheduled to launch. It's called DART, Double Asteroid Redirection Test Mission. It's going to be launched towards a moon of an asteroid to deflect the moon of a known asteroid called Didymos. And here is a radar image of this asteroid and its moon. The reason why the idea behind deflecting the moon of this asteroid, both are harmless to the Earth, so no harm can be done, is that the collision of the spacecraft with the moon of that asteroid is going to change the period motion of the asteroid around the main body of the moon around the main body by about 10 minutes. And that is something that is measurable from the Earth. So that's how they are going to be able to confirm the success or not of that mission. It's expected, if the mission is successful, about 10 minutes change in the periodical motion of the moon around the asteroid is going to be detected from the Earth. So very exciting planetary defense demonstration mission that will occur next year. Obviously, it's going to be in the news big time when it's going to happen. And it's going to indicate, are we ready or not to deal with the other objects that are out there? To put this whole picture together, we are conducting planetary defense conferences, international planetary defense conferences every other year. The last one was held virtually, was supposed to be held in Vienna, Austria, but because of COVID, it was held virtually in April, at the end of April. And it gives, if you go and visit this page, you can read about the program, about what we were, what areas were covered in terms of detection and missions, characterization, impact management, and political, legal, education, public interaction. So you can go and watch all of the recordings of the conference. The conference was fully recorded and available here for each of the 5 days of the conference. And you can visit the presentations that were covered during those 5 days and read about those presentations and read the papers or read the topics of interest to you. There were also some panels that were conducted during this presentation on different topics, all being recorded and presented. So very, very interesting resource of most up-to-date information about planetary defense by the international community. A major part of the conference is the conduction of a hypothetical exercise scenario. We had held one at this conference, and we held one in each of the last several conferences, and a few tabletop exercises that we've done since 2013. The scenario for 2021 was a relatively short warning, a 6-month scenario where we don't have any system on the ground, so we couldn't launch anything. And we essentially had to take the heat, and it made FEMA and the disaster community response very busy during the last few days of the conference. In 2019, we had both asteroid and a comet scenario. The asteroid had about 8 years of warning before impact with the Earth, and so there were a multitude of mission and campaign scenarios that were considered and computed. I invite you to go and visit those pages here and read about how the asteroid was conducted. It was an exercise. It was a hypothetical scenario, but in every respect, it was held in a very realistic fashion to a real object had it been detected. One interesting twist that was done in 2019 was a comet scenario. So the comet scenario was put there kind of just for reference. What would we do if a large comet had been detected? The problem with comets is that they come from the outer regions of the solar system. They are being detected very late in the game, perhaps a year or two before potential impact with the Earth. They usually come very fast. They are very high in energy, and they could be larger than typical asteroids. And so there is an opinion that we should pay attention to those comets. For example, this comet appeared from a very high declination angle relative to the ecliptic plane. And so no launch vehicle, no chemical rocket could intercept that object early enough to have any meaningful effect. Calculations show that we could intercept that object perhaps a week or two prior to Earth impact. And at that point, definitely you cannot disrupt it or deflect it, and disruption is very questionable. Potentially it could be done if we had a system on the ground ready to do that on a very short call, on an order of maybe a year or two. So we conducted a little study. Could we do better than chemical rockets? And so that is a study that we've done here for the PDC, for the 219 PDC. It is available to read, but I'm going to go over just the main conclusions. We tried every possible intercept with chemical rockets, and we saw that we cannot do anything with less than maybe 2 or 3 weeks, with very, very little impact to the object. So chemical rockets are out. And we use the app that I'm going to demonstrate a moment in a few minutes to show that we just couldn't do that. There's just no way we can do that. we even went wild and we said, what if we throw 30 NASA SLS rockets onto the object? So we put 30 NASA SLS rockets on it, and we were able to move it from the point of collision, which is the center of the Earth here, or a point centered on the Earth, just to about a quarter of the radii with 30 NASA SLS. Obviously, this is a no solution. So we need something else. What can we do? We looked at solar cells. And so there is this topic of solar cells that is being proposed to use the radiation of the sun, of the light of the sun, to push solar cells. So we looked at a solution that would be doing that, and we were able to find that with a particular set of steerable solar panels, we can disrupt the object at several astronomical units from its collision with the Earth at several months before impact. Now that is still in deep space, and a disruption of this object at this point could be effective. We are using a concept that is developed by a local Southern California company that puts steerable solar cells on a truss system that can be stored in a launch vehicle and deployed and made and sent towards the sun to the closest distance possible to the sun without being destroyed by the heat of the sun. And we know that there is these calculations so that this is possible. And we also look at the Parker solar probe showing that you can get very close to the sun and still function. Here's how the system is being stored in the launch vehicle. And we ran a simulation, and we found that we can intercept that comet at a distance of about 3 astronomical units at 3.5 months before impact, and try to disrupt it on its way to collide with the Earth. So we actually have a solution for comets as well, which was a very exciting study to do. So this is some of the things that we do here. Going back to the JPL website, we have an ongoing collaboration with JPL to develop what we call a Deflection App. It's an app that is encompassing orbital mechanics in it and launch vehicle performance to try to assess what can we do to deflect an asteroid if it has been discovered at a given time before impact with the Earth. So if I click on the app here, it will load the app on a website. You don't need to download anything. You don't need to do any programming. The app is ready to operate. So that is the version of the app that exists on the JPL side of the house. I invite you to go and visit it. It is a fantastic tool to realistically estimate what you could do. I'm going to give you a quick demo in just a couple of minutes and tell you how we modify the tool to support STEM education and outreach. So we created a webpage, an Aerospace Corporation webpage for that tool, which links back to the JPL version of the tool, but we created our own version that has a unique feature for teaming. So I'm going to click on this button up here, and it's going to load that tool. This is a tool that I'm going to give a quick demo on. I'm going to move this to its own page here, so we can size it on. Okay, so what you see here is a version of the tool that has one unique additional feature, which is called the team mode. And the team mode allows you to select teams among the participants, could be anyone, could be you guys, and compete with one another to deflect asteroids and see who does the best. So let's do a quick demo of the app. We hold at Aerospace, we hold a workshop to science teachers and to science students about once a month. and we team them up and create a competition between either the teachers or the teachers and the students, or even any participants that would be interested in doing. If any of you would be interested in participating in a workshop like this, or if you are aware of science teachers in your local community that would like to attend, please reach out to me and I can arrange a workshop for those that are interested to participate in our next event. Let me show you how it works. So we can turn off the team mode and we boil down to the same version that is currently existing on the JPL side, but I'm going to turn it off, and I could select a team name either out of existing team names here, or I can type out of any name that I can choose. If I do that, it's going to put the team name here. And then I'm going to set up campaign limits. I'm going to say, what's the estimated cost of each one of these launch vehicles that we have in our inventory? And how many of them I can launch at once? So as an example, I'm going to create a campaign here. I'm going to say there are 2 Atlas V launch vehicles that are available to me, maybe 2 Falcon Heavy, and maybe 1 NASA SLS. And let's say the object was discovered about 8 years before impact. I can use up to 4 launch vehicles in one campaign, and my budget is $2 billion for the whole campaign. So I'm going to set it to maybe 2 minutes here just for the demo. Typically, it will be more like 10 minutes. And I'm going to set it. Each team now is trying to maximize this performance metric. How do I do that? I go to the control panel here up on the left, and I can change the time at which the asteroid is being deflected. It's called the D date, and it's marked by this yellow line here. I can also change the date at which the launch vehicle launches from the Earth toward the asteroid. And currently, it's the launch time. It's marked by this greenish line here. And the red line is the time at which the asteroid was first spotted. And it defaults to 1 Atlas V here. So the time is ticking. Obviously, I have to act very fast. So I'm going to try to see. So I can see here that currently, I don't have any working geometry. Orbital mechanics does not work in my favor here. I have to change something. So I'm going to try to change the time at which the asteroid is deflected. You can see that those objects move along their respective orbits. And I was able to find a trajectory that moved the grid from the original impact location into a different location on the Earth. This is not a good solution. Somebody is going to complain. I have to find a better solution and move it outside of the red capture circle. It looks like I pretty much maxed on that. If I will continue to move, the green dot moves back. So I'm going to try to maximize by changing the time of launch from the Earth. And by doing that, I was able to develop a really tiny missed distance from the Earth of 0.024 Earth radii. I saved the day on the Earth at the cost of just 1 launch vehicle here. I divide the missed distance by the cost of this launch vehicle, and I find a performance metric, green performance metric of 0.122. Every team would compete to maximize this performance metric. We'll try to find the highest value by picking up different combinations of launch vehicles and times from here. And so my time expired. My performance metric here was 122. But let's say I'm going to move forward in time, just as an example in the next round, and say with telescopes, we took some additional measurements and we updated some of the parameters of the tool. For example, we found that the object is much larger. Perhaps we estimate it to be now 180 meters in size, and maybe it's heavier. Maybe it's 2.3 grams per cubic centimeter, which makes it heavier. Obviously, with 1 launch vehicle, we couldn't move it outside. We need to do something else. So I'm going to go to the campaign limits, and I'm going to say, well, now I only have perhaps 4 years of, or maybe 6 years of time available for me to deflect the objects. So I'm going to try to see what can I do. I could continue to change those times, but I could select maybe larger, heavier launch vehicles. I could try the Delta IV Heavy and select one of these. It did improve. I could select a Falcon Heavy and see what it will do. And that definitely improved. I can select both, maybe one Falcon and one Delta, and I'm almost there. Yeah, I was able to do that. Now with 2 launch vehicles, I was able to find a small launch vehicle, small small miss distance. I could try to hit it with another Falcon perhaps. And yeah, I was able to improve. So as you can see here, with those different combinations, I was able to improve my performance metric, and this creates an excitement in the classroom. Everybody wants to compete and do the best performance, and this way we excite them into knowing how to do that. We developed deflection maps. Those colorful areas tell you numbers that work. So you can pick any of these numbers here and punch it into the tool and get some performance going there during the competition. And so that was a demo of the tool. If any of you knows students or teachers that would like to participate in a workshop like the one that I just demonstrated, reach out to me and I will connect you with our corporate communication, which run those workshops every month or so. And in inspiring the next generation of scientists and engineers, again, me and my son wrote a paper where we compared natural disasters and our response and strategy to deal with natural disasters, how we would learn from these towards planetary defense planning. And so we published this paper in the Journal of Space Safety Engineering. Invite you to go and visit it, read this paper. I'm biased and I'm saying that it's an interesting paper to write and to read. And obviously aerospace would like to recruit some of those brilliant minds that might be attracted to help us on any of those technical areas, not necessarily just with planetary defense, but any space missions that are in the defense of our country. So national security, we are looking for all of these expertise here. If you know somebody who would like to join us as an intern or as an employee, you can also reach out to me. And yes, we are hiring. These are the interns that we have recruited over the years, and still recruiting going forward. And I think with that, I'm going to leave some time for Q&A and any comments and suggestions and discussion. I'm open for discussion. So I'm looking at the chat now, and I'm going from the backside. Teacher here, I'd love information about the competition, and that is from Blanca Gonzalez. So Blanca, what I can do, I can put my email in the chat, and you can just email me and I will do the rest. So let me type it here.
Thank you.
Oops, did I type it? No. Yeah, that's it. Okay, so I put my email in the chat. You can just send me an email and remind me about this event so I already know where it came from. And I will do the rest. I will connect you with our Corpcom, and we can include you and your students with the next workshop that we do, similar to what I've just shown. It's very exciting and gets energy in the classroom, and it is tied in with the next generation science standards. And so you can show, are you teaching high school, middle school, or what grade?
I teach middle school,
Okay.
and I'm a computer science teacher, but I often work with the science teacher next door to me, and so I think that would be really nice to collaborate with her on this. But I'm looking at the chat and I still don't see your contact information.
Oh, because we send it to Ellen. Okay, let me make sure that I send it to everyone. to everyone. Okay, I think that should work. Okay, now everyone should see it.
There it goes. I see it
Okay,
now.
thank you.
Thank you so much.
Okay. Okay, so let's see. There is an. I'm going from the back side, if that's okay. I'm going backward in the questions. Is there a maximum size threshold your interception and deflection systems would be equipped to deal with? That's a good question. So going back to the app here, you can see here that I can punch in the sizes here, just like I've done in the demo. And the bigger and heavier the object, the more difficult it will be to deflect. There are other considerations with respect to the size, is that if we collide with an asteroid too strongly, we could break it into pieces rather than deflect it as an object. And that is part of not knowing whether the object is made out of pile of rubble or a solid rock or perhaps an iron object. And so that brings up a very, very important element in planetary defense, which is characterization of the object. If an object allows us, in terms of warning time, it would be super useful to send a quick reconnaissance mission, maybe by a CubeSat or something like that, to simply estimate the size and what it is made out of, so we are ready for we can design the mission to respond. Once we know what it is made out of, we can then pick up out of this menu here. We can pick up if it is a porous rock or porous ice or porous rock or iron or something in between, and also estimate the size from a reconnaissance mission and see what we could do in terms of disruption, in terms of deflection. Where can we find the mathematical models used in modeling this problem? These are basically orbital mechanics models. If you contact me, I can point you to some resources. Again, all of this, you can contact me and I can point you to resources. I think the orbital mechanics here is probably something that is more suitable for either advanced high school or college level. Middle schools can operate the app. We did it with middle schools. You don't need to know any orbital mechanics to operate the app. You just need to kind of play the game here to create excitement and develop awareness. But yeah, I can point you out to resources on orbital mechanics that you could be using. Does NASA have any strategies for an asteroid to hit the Earth in 3 months, 6 months, a year, and 2 years, like an evacuation plan? I would say this is pretty much in work in progress. I invite you to go and visit the Planetary Defense Conference days 3 and 4. This is where some panels were addressing exactly the question that you were asking here, lesson learned from past disasters and public events and what we would do. There was a panel by a senior FEMA person that ran a couple of panels during days, during days 3 and 4. So there was a panel, exercise panel by disaster management discussion. What would we do for any particular scenarios? So you can either hit the presentations that were done here or just listen to the recordings from days 3 and 4 here and find the right timing for those disaster management discussions. So yeah, there are plans. I don't think that there is established process right now for these, but the discussion is ongoing, what to do. Does the ability to detect NEOs have any blind spots, such as objects that approach from high declinations? Yeah, definitely there are spots. So we are mostly looking slightly above and below the ecliptic plane, because most of the objects come from this direction. Most of the asteroids come from these directions. Comets are very hard to see until they develop a tail. And I think there are some search programs that look in three-dimensional space, but mostly it is when the tail develops maybe a year or two before coming into the inner solar system is when we start seeing those objects. There is another very well-defined blind spot, which is essentially the direction of the sun, because detection of asteroids is done with optical telescopes. We cannot point those into the sun at a certain cone of, I don't know, 30, 40 degrees. We are simply blinded. So any object that would be approaching us from this direction will not be detectable. And the object that came from, that exploded over Chelyabinsk 8 years ago came from the direction of the sun, and simply it was not detectable at all. The solar system, wind, coronal mass ejection affect asteroid speed and direction. The general answer, I think, is yes. There is something that's called the Yarkovsky effect. I'm not sure if it's affected much by the CME or the wind, but the general radiation from the sun, as it imparts momentum to the object, very small amount, but over a long duration of time, I think objects that rotate at a specific direction can be affected by the radiation from the sun. It's called the Yarkovsky effect. I'm not an expert in this, but the general answer is yes, they are affected by radiation from the sun. I'm going backward to see some additional questions here. How much confidence do we have in estimates of composition and density of NEOs? I'm thinking of asteroids, of the characteristics that Bedu exhibited, e.g. pile of rocks. They're still solid. I think that there are several methods that are attempting to characterize those objects. Very difficult to do that with optical light alone. Aerospace is another scientist and study. He looks at what's it called? What's the name of this light? I forget the name now. It will come back to me, but he looks at the light curves that would come from an object, and he can deduce some information about the rotational rate and potentially the makeup of this object. I'm going to come back to it in a minute. And then until the object comes close to the Earth, where we can use radar to shine that object with radar, is when it could attempt to be characterized a little bit better. But generally, this is the big unknown, how to characterize the object. So today, we don't have much confidence in most of those 26,000 objects. We really don't know what they are made out of, how big they are, if they are rotating. Yeah, we don't have much confidence today. What's the name of this? I'll try to remember. Okay, I'm going back in the questions. By the way, I received an email from Blanca Estela Gonzalez, so your email has been received. Has the planetary defense community decided on collision risk probability threshold to initiate a deflection answer? It's an open question, but what we generally have exercised at conferences and exercises is 10%. So if the object likelihood of collision has risen above 10% is when we start to take it seriously. How do we calculate this? Basically, because those are exercises and all of the objects are simulated objects, JPL conducts what is called Monte Carlo studies. It invents an object on a specific orbit, and it varies the uncertainty of the object based on non-telescopic characteristics. This is how a specific telescope let's say pan-stars or a goldstone would detect the object, and they vary those characteristics and create sort of like a uncertainty region that evolves over time, and see how many of what portion of the region hits the Earth. So if the Earth hits 10% of the region, then there is 10% of collision with the object. And that's how they figure out the percentage. If you go back to our exercises here, let's see, where was it? Yeah, so if you go back to those exercises, I'm going to go back to the 2019, and you can read day by day how that occurred. And so, for example, at the start of the conference, you can see that this region of uncertainty extended much beyond the orbit of the moon. And so the likelihood was very, very tiny with this object. But if we're to move to the following days, so this is an 8-year scenario that was collapsed into 5 days of the conference. So each day is a certain number of days or years ahead. And so you can see here is that based on a telescopic detectability, there are regions where the object is simply not observable, goes out of view. And so the next opportunity to see the object will be maybe a year or two later when it comes into view based on these calculations. And every time an observation is being made, the estimate of the likelihood is refined. So, and you can see here, let's see what they had here on day 2, press release. So we exercise press releases just like the way they would be published in a real event here, telling you what will happen on this day. This is the information that NASA would be putting out on a real event that will be similar to that particular situation. The briefing, I think, maybe gives a better estimate of the region here and the consequences. Let's see if they have this map here. Okay, so the region is still very large. The region still extends much beyond the region of the moon. Let's go forward a day, see what this briefing will give us here. Here we start to talk about the consequences here. What could be caused on the ground in terms of casualties and devastation? NASA Ames does a lot of those calculations. We develop regions of evacuations here or potential impact, essentially impact corridors. As you can see here, now they are narrowing down to specific regions on the Earth. And these are the locations that could be impacted by this object. And these are the populations that would be affected. Some cases could be well in the millions, right? New York City and big cities could be affected by these objects. Everything is invented here, is simulated, but it's very realistic. So that's what we do here. Let's see, let's go back to more questions here. Does the loss of Arecibo telescope affect our ability to detect and track potential news? The answer is yes. Arecibo is a big loss here. It was an essential tool to discover. So again, I'm not expert on this particular aspect, but my understanding from talking to other people is that it's a big loss to our ability to detect those that we should recover with probably space missions. I don't know if they're planning to rebuild any of these, but it is a big loss, my understanding. Have there been any published efforts to verify the estimated state uncertainties of asteroid comet orbits? Yes, I think these are topics of research. There have been many studies that have been presented at the conferences. The Planetary Defense Conference will have a few, I think JPL has, let's go back to the JPL impact risk. So they have this tab here about impact risk that you can go and visit and see what has been done to estimate those likelihoods. Those objects are residing on their center here. It's called Sentry and Scout. And here you can see the table of those likelihoods. You can, oops, something crashed here on my side here. My browser crashed on me. Let me try to recover that. Okay. All right, so going back to this page here, this is the Sentry Earth Impact Monitoring database that JPL maintains with those potential impacts, the probabilities associated with them, and the years. And you can click on any of these objects and load additional information about it, how it was discovered. And I think that they do have some additional documents and resources that might tell you how things are done and talk about those probabilities. So, and this is just starting points for many other papers that tell you how those things are done and how the calculations of those probabilities go. Let's see, hoping I'm answering those questions. Okay, I think I'm coming to the top of the questions. Let's see if there are any new questions that were. Some comment here, spectrographs for Doppler curves. Yeah, again, this is outside my area of expertise. I believe that these things are done. How do you call these lights that are? I forgot the characteristic of this light, but so there's a study that was done to use visual light to characterize those objects. But yeah, my answer is yes. Okay, any other questions, comments, contacts?
Looks like we exhausted our questions. There's maybe one more just posted right now.
Okay, can anything be done to alleviate the effect of the moon wobble that NASA has mentioned this week? No clue. I don't know.
Yeah, there was a posting about the moon wobbling and therefore potential increase of the flooding to the affected areas. But I am not sure if there's anything can be done because of a moon wobbling. Yes.
Not with things that are related to defense from asteroids, I think. I don't know. Okay, yeah, you can contact me at any time if you wish. You have my email for service help with moon wobble.
That was, yes, that is just now a discussion of the engineers that potentially how the side effect can be in a turn into a positive effect. Yeah, that is, who knows, right? A lot of United States area is under tremendous drought. So maybe that will affect in somehow impact in increase of rain in the area where they need rain, because those that are joining right now from Houston area, they know that is something that we do not need in there because it's been raining nonstop almost practically for almost a month. I wanted to express thank you and gratitude, Nahum, for joining today and sharing your knowledge and presenting and also demonstrating various resources that we can, as engineer community, can reach out and perhaps either dive into it more and learn more or use that material for further research and development. So thank you so much for showing, demonstrating what is available and how much more can be discovered.
Thank you very much for inviting me, and very happy to collaborate with anyone. And I think somebody's want to say something or...
Yes.
Okay.
Thank you. So Svetlana, I want to make sure that on the ASME side, we make PDH certificates available for people who get PE credit for attending. And if you're one of those that would like a PDH certificate for attending tonight, please contact me tonight or tomorrow and I will send it to you. I don't have the RSVP list for this meeting because AIAA does things differently and there was no RSVP list. So please, you can email me at ellengillespie@asme.org, or you can use asme.secretary.text@gmail.com, but send me a message and I will get you a PDH. Thank you.
Thank you, Ellen. And also wanted to mention that this, we will post the recording of this presentation and it will be available on both AIAA Houston Section website, as well as we'll post it on the SpaceGeekSpeak YouTube channel. So then it will be easily accessible by all the members of all three societies, as well as other interested parties. So with that, thank you very much. Really appreciate everyone's engagement and attendance. And please join us at SpaceGeekSpeak on Saturday mornings if you're interested. The information about that event is posted on AIAA Houston website. And look forward to future events that we co-host or all the other societies host independently.
And one last question for me, Svetlana. Would you like me to send you the list of those websites that I visited today, if people are interested to kind of dig more depth into them and read more? So sounds like this might be useful. I see a lot of thank yous on the chat here, and I'm saying it's my pleasure, it's my duty, you know, as someone who is dedicating a lot of my time into that. So I'm saying thank you for letting me talk to you and inspiring you. Be happy to talk to you more. I'll send you the list of those web pages and you can share it with everybody.
Absolutely. And I will post it both on the website, on our AIAA Houston website, as well as on the YouTube channel. So then that relevant information to this presentation. Thank you again. And thank you everyone for joining us. This concludes our meeting and we're looking forward to our next year meeting that will be hosted by IEEE, right? Yes. Okay. Thank you so much. And again, it's been a pleasure.
Thank you everybody for your thank yous. I'm very happy to see that.